In the name of God, the compassionate, the merciful. Engineering Plasticity, Chapter 3, Yield Criteria, Part 8. I'm going to wrap up this chapter with a more Coulomb model for ductile materials and for brittle materials. Okay, Moore Coulomb model is another model for the yielding of materials. Now, which materials? First of all, let me explain this. This is the vertical axis and horizontal axis. This is the shear stress, that's the normal stress. This is usual drawing of the Moore circle in this axis. Now consider a ductile material which has higher yield strength in compression than in tension. Now I have mentioned before in the introduction that some materials exhibit from themselves different yield strength values in tension and compression. In other words, if you test this kind of materials in tensile test, you get value for strength, yield strength, and if you test it in compression, you will get a different value for the yield strength. Sometimes the yield strength in tension is higher, sometimes the yield strength in compression is higher. For instance, for the civil engineers, the cements, the cement material, usually the compression strength is higher than the tensile strength. Okay, so this may be more used to the civil engineers, but still we have also in the different materials that we are using in the mechanical engineering with this kind of behavior. Okay, so here we are considering that this material, which is ductile, has higher yield strength in compression. So if I draw a circle here and show SYC, this circle shows the limit for this material. In other words, the maximum shear stress is that value, that's the maximum shear stress, and this is the maximum normal stress. So because I have tested the uniaxial tension, so the maximum yield strength it could have is SYC, Y for yielding, C for compression. Okay, so this is for the compression test for this material. And this circle shows the strength, yield strength of this material in tension. So that's positive and that's negative. Negative compression, positive tension. Obviously the size of circle is smaller than that, showing that SYT smaller than SYC, as we have mentioned here. So this shows the behavior of this material in tension and in compression. Now let us draw this line tangent to both circles. If we draw a line tangent to both circles, it will intercept sigma axis at a point like this. So we get an envelope like that. Obviously, this is symmetrical. We can draw also a line like that over there. But for the time being, I just want to deal with this part of the figure. Okay, so that is the envelope containing these circles. Now, if I consider a loading condition which is in between these two, in other words, if I push the circle to the left and the size of the circle is that, I would be in the limit. I mean the material would be in the limit of yielding that point. And if I push the circle to here and reduce the size, I will get the other limit, which is SYT. But somewhere in between, like this circle, shows the loading condition for the material which has not yielded in compression or in tension, somewhere in between. Okay, note that I have put it in the envelope. I have not, this circle is not higher because that is the limit. Now, sigma A and sigma B are two values for the material under tension and compression. And if I now draw some lines like these yellow lines, this is the center of the big circle here. So because this is tangent, if I draw a radius here, it will be perpendicular to this tangent. Similarly, I could draw lines for the blue circle, okay, which is the loading case, then that will be perpendicular, and also for this smaller circle that would be perpendicular too. The reason I'm doing this is that because I want to find out the relationship of these loading conditions to the yielding points. In other words, I find the yield criteria from these figures. Okay, so let's see what are these values. Now from here to there is the radius of this circle. This circle is supposed to be tangent at this. So the radius of this big circle is SYC over 2, and the radius of the smaller circle is SYT over 2. And also we could find out the center of this circle. Remember, this circle is the loading case, and we have sigma B and sigma A here. So the center of the circle has this coordinate, sigma A plus B divided by 2. And this line, yellow line, is radius of this circle, so it's SYC over 2. And this yellow line is the radius of the blue circle, is sigma A minus B over 2. And similarly, the radius for the smaller circle is SYT over 2. And if I draw a line from the center of this circle parallel to this line, since this line is perpendicular to that, this line will also be perpendicular to that, to this O prime M is perpendicular to this yellow line, also to this yellow line as well. So I get a triangle here like this, which I have called O prime M with this CM in here. So if I have a look at this triangle is something like this. Okay, so I want to see what the lengths of each parts of these triangles are, and then find some relationships. Okay, I have a look at this in here in more detail. Let's have a look. Now this OM, how much is it? Is SYC over 2 minus SYT over 2. Why? Because this SYC over 2 is SYC over 2 is this yellow line. Okay, now this has been perpendicular to this, so that yellow line with that yellow line is equal. Therefore, if I subtract this part from all of it, I will get this part, or I will get OM. So OM is SY C over 2 minus SY T over 2. Similarly, I can get other parts like Cn, like this Cn. I can get it because I have this radius is sigma a minus b over 2 minus this part, which is Sy T over 2. Okay, so that's Cn. And similarly, I can get this line OO prime. OO prime is Sy C over 2 plus Sy T over 2. And this line O prime C. O prime C is Sy T over 2 minus sigma A plus sigma B over 2, because this is the radius, the center of this circle, of this blue circle, and clearly I have this SYT is positive and this is negative, so I get this value for the center of this circle. Okay, I mean O prime C. Okay, the value of O prime C is Sy2 over 2 plus this value was because sigma A plus B over 2 is negative value, so we write it like this. And therefore, in this triangle, we have Cn and OM perpendicular to O prime M. Therefore, 90-degree triangles and also similar triangles, because these angles are also equal in here and there, and this is common to both of them. Therefore, we can write, for instance, Cn over OM is equal to O prime C over O prime O. So we can write these similar triangles. For instance, OM to O prime is equal to Cn over O prime C. So just by playing with the denominator and numerator, we get these values. And if I rearrange these sentences and simplify it, I will get that sigma A over Syt minus sigma B over Syc equal to 1. This is the yield criteria for more Coulomb, for ductile material, obviously. And now here we can use these yield criterions in design problems. And as you know, in design problems, we usually use a factor of safety like n. And so if I divide this 1 by n, I will get, I will incorporate the factor of safety into this equation, which is this. Okay, so the yield criteria with the factor of safety will be that. And let's see the condition for this equation. If, for instance, we have a loading case like that, okay, loading case like a smaller circle, it is in the envelope, and so does the yielding occur or not? Well, obviously, looking just at this circle, yielding would not occur, but this is what, in plane loading or out of plane loading. So out of plane loading and in plane loading, both of them come like that. So if we put this circle as well, then we will see that it will yield because it's outside this envelope. So there is a condition for this to be true. And the condition is that sigma A should be positive. For this circle, it is positive, this point. But also, sigma B should be negative. So this sigma B, which is this one, should be negative. So the loading case should be something like that. Some part of it in the negative part and some part of it in the positive part of the diagram. Otherwise, it won't be, it won't hold because this circle is in plane loading and out of plane loading is this circle. So that's why we should have a condition like that for this. Okay, now let us also consider some other cases as well, like this. Supposing we have a loading condition like that. Okay, so here sigma A is positive and sigma B positive. So is it does it hold for this criteria or doesn't? I mean, does it yield or not? In fact, it is on the verge of loading because the out of plane loading is that, the circle, and so as you can see, we are on the verge of yielding, the incipient yielding, and if we go a bit further here, it will yield. I mean, a bigger circle here, it will yield because the out of plane loading will be bigger. It will go out of this line. Okay, so that is the extreme case. Let's examine the extreme case. The extreme case here is this one. It's this one, and for this one here we have no SYC. So SYC is 0. So we get sigma A over SYT equal to 1 over n, and then condition for this equation is that sigma A greater than sigma B greater than 0. So that's sigma A and sigma B greater or equal to 0. And this circle should not go out of the SYT. So that's how we get a special case of this one. And also, let's examine the other case over here. If we have a compressive stress like that, so we are on the verge of yielding in compression, and then out of plane loading in plane loading, and you see again here we are on the boundary of yielding. So here, because this circle, both of them are over here in the negative side, so SYT here is 0, and we get sigma B over SYC 1 over n. Of course, here we have this negative for the compression side, and this is what we have, and the condition is this: sigma A minus B. That here for this circle, sigma A is this one, and sigma B is this one. So sigma A is smaller than sigma B, is smaller than 0. Then perhaps we could say that this is the threshold. These 2 points, this point here, SYC and SYT, are the thresholds. We cannot go further from here or further from there, okay? Because the out of plane loading, the circle corresponding to out of plane loading will be greater than this envelope. It will go outside the envelope. As the circle goes out of the envelope, it means that it will yield. So these are the extreme points. SYC and SYT are the extreme points. Note that this circle and this circle are different cases of loadings. It's not like the in-plane and out-of-plane loading. This is just a uniaxial tensile test, and then this is a uniaxial compression test. Okay, two different kinds of loading. They are not the same loading like this one or the other ones that I showed you. Okay, so this is how we look at the Moore Coulomb model for the yielding of ductile material. I will talk about this later on to illustrate it for the brittle material as well.